Hi, my name is John Wakefield. This is the first lecture on subnational modelling of health indicators. In this lecture I'm going to cover complex surveys, small error estimation and weighted estimates. Here's an outline of where we're going. So I'm going to motivate the need for subnational estimation, then talk a little bit about complex survey sampling and then small error estimation. Then we'll come to different summary measures we might want to look at, and then we'll look at a case study on subnational neonatal mortality estimation in Rwanda. And finally, I'll summarise the lecture briefly and say where we're going next. So, to motivate the need for subnational estimation, so for purposes of programming and interventions, and to monitor progress toward targets such as the Sustainable Development Goals, subnational estimates of indicators of interest are desirable. And there are many things we might want to think about, and we can distinguish between simple prevalences such as neonatal mortality or having a vaccination or not, or stunting, and compare those with more complex variables such as under 5 mortality, fertility or maternal mortality. We're going to focus on the first set of simple prevalences in this lecture, so just binary outcomes, yes or no for some particular attribute. Now, for many health and demographic indicators, there's considerable within country variation. So if you look at a variable like a vaccination rate across areas, across districts, you'll see large changes across a country. Large differences. So the idea behind small error estimation is the task of estimating a variable of interest within geographical areas based on potentially sparse data. So this is the small within small error estimation. It's not geographic small, it's is there a sparsity of data. Perhaps in some areas we have no data at all. And then the notation here I'm going to use is when I refer to admin 0, that's going to mean the national level. Admin 1 will be 1 below national, admin 2 below national, admin 3, 3 below, etc. So here to show you that here's 3 levels of geography, nested geographies for Rwanda. So the national level would be the whole, that's admin 0, that's the whole country. Then we have 5 admin 1 areas here, 30 admin 2 areas in this top right, and then we have these 422 admin 3 areas in the bottom left. So in low and middle income countries, household surveys are often the most reliable data source, but they are not powered, i.e. designed to produce weighted estimates at fine spatial levels. As we'll see, weighted estimates are going to be the method we'd like to use as much as possible, but we don't have sufficient samples to gain the required precision when we start moving through the geographical levels. So to overcome this, many different types of small error estimation smoothing models have been developed. And there's 2 particular types I'm going to talk about over this series of lectures. One is area level models that are quite easy to implement and quite robust to modelling assumptions. And those often work very well for admin 1, sometimes for admin 2 also, but then as we go lower, then we're not going to have the basic ingredients we need to be able to use those models, as we'll see. In that case, we need to turn to unit level models, which are based on far more assumptions, but they use the data much more efficiently, at least when the assumptions are being met. Now, if you want to read up more on these models, I recommend the book by Rao and Molina. That's the classic text on small error estimation. Now, a key point that I'm going to emphasize over the next few slides is that all the models or the approaches we use have to acknowledge the survey design. So as we'll see, the designs that are used within low middle income countries are quite complex, and so we need to make sure that the way we analyse the data is consistent with the way the data were collected. And here I'm going to distinguish between 2 particular approaches to inference, 2 really quite different approaches. One is known as design-based inference, and that's what's used a lot within the survey sampling world. And then there's the model-based approach, which is used more. It's more of a conventional statistics technique, which has been moved over into the survey sampling world. And survey sampling it's a huge topic, and it can be complex. So if you want a recommended text here, I highly recommend this book by Sharon Lowe. It's a very nice book, now in its 3rd edition. Okay, now I'm going to talk about complex survey sampling. So the DHS uses stratified 2-stage unequal probability cluster sampling. So the strata here consist of urban-rural crossed with geographical areas, usually admin 1, but sometimes admin 2. Then within each strata, enumeration areas, or I'll use the word interchangeably with clusters, are selected with probability proportional to size. So the number of households here is the size variable. So enumeration areas with more households are more likely to be selected. And the sampling frame here is, which has a list of the enumeration areas, is based on the most recent census usually. So the unequal probability sampling part here is that not every enumeration area is equally likely to be selected within each strata. And then within each household, within each of these selected cluster, households are selected, a constant number of households typically, or maybe sometimes different in urban and rural, but that number is selected, and then participants in that household are interviewed, and that's what supplies us with the data. And now, given all those steps, we can define sampling probabilities, what I'll call these pi IKs here. They are the probability that a particular household or individual was selected in area I. Okay, so here is two maps of the same map, just with different geographical boundaries. So on the left we see the 5 admin 1 areas of Rwanda, on the right the 30 admin 2 areas, and then those dots are just the different 3 different surveys that were carried out in Rwanda: 2010, 2015, 2019. Later on we'll just focus on the blue dots, which are the 2019 samples. And so in the 2019 Rwanda DHS, stratification was urban-rural crossed with 30 districts. Taken from these enumeration areas were taken from, that listing was taken from the 2012 census. And then 500 enumeration areas were sampled, of which 112 were urban and 388 were rural. And then within each of those 500 clusters, 26 households were selected to give a total of 13,000 households. Here's another map of Rwanda. This time I'm showing in green the urban areas, and in grey the rural areas. Now, just want to explain here a little bit about why we need to adjust for the stratification. So suppose we're interested in the proportion of women aged 20 to 29 who've completed secondary education, then, you know, so might expect secondary education is higher in rural areas than in urban areas rather than rural areas rather. So the prevalence of secondary completion is higher. So if we oversample urban areas, which is what frequently happens in the DHS and also in mixed surveys, then if we just ignore that when we do the analysis, that's going to lead to bias. The reason being is that we've got urban women are overrepresented in the sample, and so we need to downweight those women to balance up the sample so it's more representative. And so in the design-based world, that's done via what are called design weights. And we'll see there's other techniques we can use when we use a model-based approach when we look at other models later on in later lectures. Just another note here that we also need to adjust for the variances need to acknowledge the stratification as well, and that's done with specific calculations which have been, particular formulas which have been developed for those that particular sampling scheme that's used within the DHS. Okay, so that's the stratification aspect. The other aspect here is cluster sampling, and so because we've got multiple individuals within the same cluster, and clusters are more likely, people within the same cluster are more likely to be similar, we effectively have less information from 2 women in the same cluster as we do from 2 women in different clusters, because women in the same cluster share a lot of common environment, etc. And so again, we need to adjust for this when we do the variance calculation, because we're not just interested in point estimates where we reduce the bias, but we're also interested in a measure of uncertainty. So small area estimation is going to be the next topic. So I'm going to distinguish here between 2 situations. The non-complex survey sampling setting, so that's the more regular setting that people are probably more used to. So I'll describe that first, and then we'll just contrast that with the survey sampling setting. So when we're presented with data, we often assume that they're implicitly from just a simple random sample. And so in that case, and in this situation, we often think of the parameter of interest as from some hypothetical population. So we imagine there's an infinite population we've drawn a sample from, and then we calculate the proportion, some empirical proportion, and that's really targeting the proportion within some infinite population. So in a survey sampling setting, there's 2 things that are different. One is, rather than having simple random sampling, we have a complex design, such as we've just seen, stratified 2-stage unequal probability cluster sampling. And then we have, rather than a characteristic from an hypothetical infinite population, we think of a finite population characteristic. And in this second setting, we need to think of specific methods which will acknowledge those 2 aspects. So here's back to the non-survey sampling setting. So suppose now we're interested in, let's say, neonatal death. So we imagine in this setting, we take a simple random sample from some hypothetical infinite population. So we imagine there's an infinite number of people in area I, and what I'm going to call the risk is the proportion of those infinite births that occur in area I, which result in a death, a neonatal death. So death in the first month of life, and call that Ri. And so that risk parameter Ri is the proportion of events of interest in this infinite superpopulation who we imagine living in area I. And then just to give some notation, Yik being 0, 1 is the indicator of an event occurring. So when we go out, these are random variables, we go out, we sample, say Ni is 100, we sample 100 births, and then we follow them for a month. And if the baby lives to the end of that month, they get a 0. If the baby dies, they get a 1. And so then what we do is we might assume, okay, the total number of deaths, just add up those 0s and 1s, so add up all the 1s. We might assume that's a binomial with little ni, so 100 trials and some probability that each one of those births will lead to a death. And then the obvious estimator is just the total number of events divided by the sample size, so that's just in this formula here, because this will lead into what we're going to have on the next slide. And then the standard error is just this standard formula from this binomial assumption. We've got this standard assumption that we've got this this formula which allows us to get standard errors and confidence intervals, etc. Now let's contrast this now with weighted estimates and what I've called prevalence. So the prevalence PI is the empirical proportion now in a finite population which has a certain condition. So now Ni is the total population size. So what we're trying to target here now isn't some infinite population proportion. Rather, it's a finite population of size big Ni. And we know there were TI true deaths in that population. But we are just going to take a subsample and then we want to try and infer this prevalence PI based on our subsample. So the difference between risk and prevalence, risk is this hypothetical infinite population. Prevalence is with respect to a finite population. And of course, if we were to take a complete census, i.e. sample all Ni and see all the subsequent life history of those babies, then we would not need statistics because we'd know the answer because we've seen everyone. But of course, we don't see that in general. But in that scenario, even when we see everybody, in the risk scenario, we don't know the true risk because the risk is pertaining to some infinite population. Okay. So again, with the same notation, we've got these 0s and 1s. Now in the survey sampling setting, let's define this super important quantity called the design weight. So the design weight is 1 over the probability of being selected. So remember, through that sequence of stratification and this multi-stage sampling, we had every unit we sampled, every birth we sampled had an associated sampling probability. That's the probability that we were to get to observe that. And that was different because of these different probabilities of being sampled in different strata and different enumeration areas being sampled. So now, this weight can be thought of as the number of people represented by person K. So imagine if you had a sample of size 100 and there was a 1 in 10 chance of a particular person being sampled. Say it's equal, suppose it was simple random sampling in this case. Everyone's got an equal chance. Each one of those 10 people sampled out of 100, if it was simple random sampling, has design weight of 10. 1 over a tenth, which is 10. And so they're each representing 10 people. Then the weighted estimator is just this weighted mean. So rather than previously, we had this sample mean here, the sum of the y's divided by the sum of the sample, now by the number in the sample. Now we have this weighted combination. So it's an average again, but it's a weighted average. And that's this weighted estimator. And it's known as a direct estimator in the survey, in the small area statistics world, because it uses data directly from that area only. So later on, so no data from any other area is contributing to this particular estimate. So later on, we're going to look at estimators which are called indirect estimators, and they use all of the data together to estimate the prevalence in each area using all of the information. So this big green box here shows how important it is. So the weighted mean is the direct estimate, and it's going to be the method of choice for producing subnational estimates. Okay, so the advantages. The weighting can be used, those simple weights can be used in both that weighting formula and also when we calculate standard errors to acknowledge the different elements of the design. So to remove the bias and get the correct level of uncertainty. It's based on very, very few assumptions. There's no model I wrote down there. I didn't write down a binomial or anything like that for that formula. We just basically directly wrote down that weighted estimator. And it's often great for admin 1 or even admin 2 estimators. The weighted estimator often can do a job for us, but there are some disadvantages. So when the data is sparse in an area, then the estimator is going to have unacceptably high uncertainty, so very low precision, and then we need to move to a different approach. And in the limit, some areas will have no data at all, and then of course there'll be no estimate available. And here's just a little picture I always have in my mind about how you're doing small area estimation. So if we have sufficient data in a particular area, then we can work out the weighted estimator. If the answer to that question is no, we don't have sufficient data, then we need to go to some different approach, and that's where we're going to cover in later lectures these two different types of approaches, area level and unit level models. So after we have calculated our weighted estimates, there are various ways we can report them and their uncertainty. So we all have to look at maps, and so a map of the prevalence estimate is what we'll probably look at first, but alone it can't tell us too much because we need to know about the uncertainty associated with each of the points that we're mapping. So to make interpretation and take action, we have to understand about this variation. There's lots of different ways we can think about that, and so I'm going to talk through about the standard error, which you're probably familiar with, stating an uncertainty interval. The coefficient of variation is in a sense like the standard error, but a standardized version of that. The width, then we can look at the width of an uncertainty interval, and then we can also examine something called ridge plots. And as we'll see, I'll talk through these now, but they're going to be of interest for other things we look at later. Okay, so as I mentioned, we obtain our weighted estimate, that pi hat w, so that's the weighted prevalence estimate from the survey data, and then using other survey sampling techniques, again based on the weights, we can come up with a variation associated with that estimator. And so the standard error is simply the square root, and then we do this in many other things, models as well. We can look at, for example, in large samples, so if the sample size within the area I is sufficiently large, and that's a very, that's a wishy-washy phrase, but there's no really hard and fast rules for when the sample size is large enough, but we can look at plus or minus for a 95% confidence interval with sufficiently large samples. This interval here, so under repeated use of this formula, this will cover the true prevalence with probability 0.95. And so we look at the estimate plus or minus 1.96 times the standard error, so just a standard confidence interval. And the width of that interval is just given by 2 times, roughly 2, so 4 times the standard error. So that width is just an overall measure of the uncertainty associated with that error. Rather than having to look at the lower and the upper, we could map this, for example, the width of the interval. Now notice that the width of the interval here, there's no pi hat w in there, so it doesn't depend on the point estimate. And that is a drawback for something that's got this limited range like a prevalence. So, for example, suppose I give you an interval width of 0.1. That means very different things depending on whether if we've got a prevalence estimate of 0.5, then the interval is 0.45 to 0.55. So we might think, oh, that's reasonable. Whereas if the prevalence is 0.05, that gives us an interval of 0 to 0.1. And, that's a lot of uncertainty for a relatively rare event. So something that tries to get over that lack of dependence on the point estimate is known as the coefficient of variation. And this is very popular in small area estimation. So the coefficient of variation is given by the standard error divided by the point estimate. So the estimate, the standard error, so that's square root of v divided by pi hat w. And there's a couple of examples here. So if we have a point estimate of 0.1 and the standard error is 0.05, then we divide one by the other, multiply 100, then the coefficient of variation will be 50%, which is quite a large number, and that reflects the fact that's the example we just saw. We've got a standard error of 0.05. That's a large, that's similar to the example we just saw. That's a relatively large standard error, and so we're excuse me, we in this situation we'd view our information in that area as being quite unreliable. Whereas if the point estimate is 0.5 and the standard error is again 0.05, then the coefficient of variation is 10%, because then we've got relatively narrow, we're very relative to the size of this value, we're pretty close by. And some agencies have criteria for reporting. For example, Statistics Canada, they say if the coefficient is less than associated with a particular estimate is 17%, then we'll call that estimate reliable. If it's between 17 and 33%, we'll view it with caution. And then if it's greater than 33%, we'll call it unreliable. Now, it's always hard to stick, have these hard and fast rules, but these guidelines, are something to keep in mind. It always depends, but basically, is the estimator fit for purpose? And so we have to examine the uncertainty to do that. And so, as I mentioned here, since the coefficient variation is an explicit function of the point estimate, this often will be a preferable measure to the width of an interval. Because note, the confidence interval depends also on another point, and a different point is that the confidence interval depends on a level such as 0.95. We could have a confidence interval of 0.8, whereas the CV, the coefficient variation, is independent of all that. Finally, on this section, ridge plots, as they're used in small area estimation, show the complete range of uncertainty for a collection of areas. And there's many different ways we can use these. So, for example, we can look at all the admin 1 areas stacked on top of each other. So, as a prelude to what's to come, here's such a plot for Rwanda with the 5 admin 1 areas, and we can see this is for neonatal mortality. So the highest rates are in this area here, the lowest here in Kigali. But there's quite a lot of uncertainty you can see from the overlap in these distributions. We can also look at admin 2 areas within a particular admin 1. Often there'll be many areas, and it'll just be too larger vertical line for two. So then we can just say plot the top 5 and the bottom 5, or something like that. And the way these are ordered, we can order them in different ways, but we could order them by point estimate, so increasing or decreasing, or alphabetical going upwards, as in here. So there's different ways we can do that. Okay, so now let's look at an example. So here we're going to look at neonatal deaths, the prevalence of neonatal deaths, so death in the first month of life over the past 10 years before the 2019. So the 2019-2020 Rwanda DHS, in the previous 10 years, mothers were asked whether they had a child that died within so how many children they had born, and then if any of the children died within the first month of life. And so we analysed these using the Shiny app. They can also be done with the Survey Prep package, but so just to give some context, so the national weighted estimate in Rwanda is 21 deaths per 1,000 live births, so that's 0.021 in terms of a prevalence. And the standard error, so 21 deaths, and the standard error of 1.4, which is quite small, which we'd expect because it's a national estimate, so it's based on all of the data. And the 95% confidence interval is 18 to 24 deaths per live births, which is a width of 6. And the coefficient of variation, if we divide this 1.4 divided by 21, multiply by 100, we get just under 7%. So that's a very low coefficient of variation, so highly precise estimate at the national level. So that gives us a context now. So as we said, we use this stratified 2-stage cluster sampling, urban rural areas crossed with, in this case, the 30 admin 2 areas. And we sample areas. We've seen all this before, but just to remind, so here are the clusters, the number of clusters. So the smallest number of clusters are in Kigali, and then the largest number in this area here, and then intermediary in the other 3 areas. This is at the admin 1 area. These are all the number of clusters sampled. Remember, there was 500 in total in Rwanda in that survey. So here again are those ridge plots. So we can see, the highest estimates in this Amaj Yepfo. And then Kigali had the lowest estimate, and then these 3 are the ones in between. Now, the first thing to say is even at this admin 1 area, which is a pretty, coarse, only 5 areas, we still get a lot of uncertainty. See, the range here is quite large in the point estimate, but there's a huge overlap between these distributions, suggesting quite a lot of uncertainty even at the admin 1 level. And that's the reality, particularly with rare outcomes. Even with a relatively large survey, we're going to see quite... So I think there's 13,000 households here. We're going to see, because it's a rare outcome, they don't have that much information on NMR here. This is the map of the point estimate. So we see Kigali with the lowest estimate, that's 0.013, the highest estimate over here, 0.029. So that's a large range, right? More of a doubling in, at least in the point estimates. So there's large between area uncertainty, and there's large between area, that there's uncertainty within areas, and between areas there's large variation in the rates. But we need to know, we need to calibrate these numbers by the measure of uncertainty. So here, again, there's our map with the names on them. So this is a screenshot from the Shiny app. And then here here's the mean estimates as we've seen before. So ranging from 0.0, well, we've seen these on a map between 0.013 and 0.029. And then here's the standard errors. Are quite, they look quite small, but here's the upper and lower confidence bands. The width of the confidence intervals are quite similar, even though the range of estimates is quite large. But we see the coefficient of variation is quite a lot of spread there. So ranging between, what's the lowest there? 12.6% up to 24%. So a doubling in the precision across, as measured by the coefficient of variation, with the lowest precision in Kigali. And of course, that's the one with the lowest rate, and so that makes sense because the coefficient of variation is the standard error. So it's this number here divided by this number here. That's where we're getting those from. Okay, so here we can plot the coefficients of variation. We see here Kigali with the highest, and this area here with the lowest. These are looking at the width of the confidence intervals, and as I noticed, they're all very, very, remember from the table, they're all very, very similar here, between 0.11 and 0.14. So that's very, very similar. So as I mentioned in the earlier slides, the coefficient of variation map is more useful as it tells us about the relative uncertainty relative to the point estimate. Then finally, here, this is the probabilities of each area exceeding the national estimate of 21 deaths per thousand. So imagine we draw a line here, and then we're evaluating the probabilities to the right of that line. So for example, for Kigali, that's going to be close to 100%, and this is of exceedance, so 100% of the curve is below that 0.021, and we see that here, these very low values here in this area, also in this area here, which is this one. So imagine we're drawing a line up here, and then at 21 or 0.021 here, and we're looking at the amount of mass to the left of that point. That's the probability that it's less than. So the exceedance is 1 minus that. So we see this area here has got the greatest. So this is the area here with the greatest point estimate, and we see there's quite a probability, a large probability that we exceed that value. So that's just another way of showing that the uncertainty in each of these estimates. These all are different ways of showing the uncertainty in each of the areas. Okay, so just to summarize, so in this lecture we've motivated the need for special methods when we have complex survey data, remember, because of the complex design, and we're also looking at finite population characteristics, these empirical proportions, i.e. the prevalence. So the basic weighted estimator was seen to be had very nice properties, and it's a very desirable estimator if you have sufficient data to use to answer, get you as precise an estimate. So in this last example, it's pretty good. You don't have anything above 24% coefficient of variation. So for admin 1 level, it's a pretty powerful estimator. But as we'll see in later lectures, admin 2, it's not as good, because as you drop down, you lose, you get fewer and fewer samples per area, and so then you get lower and lower precision. Then we presented a number of summary measures and illustrated their use and interpretation. So next up, now we've seen these, as I just said, the weighted estimates are okay, but often we want to drill down to lower levels, and then we need to do something more. We need to start some modelling, and that's where small area estimation methods come in. And we're going to look at 2 classes of models. So area level models, which basically take as input the weighted estimates and then smooth across areas. So take all the data together and then smooth, lose information in the neighbouring areas. Say if there's similarity, we can smooth. And then unit level approaches, they're the most powerful in terms of getting the most precise estimates, but they're also the most dangerous to use because they're based on the most assumptions. So yeah, that's this lecture done. There's my email, jono@uw.edu, so don't hesitate to get in touch if I can help answer any questions. Thank you.